Okay, good evening. Welcome to Math for Kids number 20. Today we're going to talk about the continued fraction for pi. I'm going to try to write a little bit darker. Okay. All right, the continued fraction for pi. So first of all, do you know what pi is? I know you've heard about it before.
I think it's 3 1/4.
What is pi? Well,
it's the 16th letter in the Greek alphabet.
Yes, it's the 16th letter in the Greek alphabet. Okay, great. Pi, if you take a circle and you take the diameter, it's the ratio of the circumference
I haven't heard what ratio is.
to the diameter.
Is the ratio how from the edge to the diameter?
The ratio means you take how long the circumference is, and you divide it by the diameter. So it is, here, can I have your purple marker for a second? It's how many diameters it takes to go all the way around the circle. So if I have a line that's this long, or a line segment that's that long, so I'm going to go around once, 2 diameters, 3 diameters, and then I have a little bit left over. Just a little bit more.
I think that's 3.
So it's just a little bit more than 3. Okay? So today we're going to talk about, a lot of people really like pi. Do you like pi? A lot of people like pi, and a lot of people in math like to talk about pi and study pi. So today we're going to talk a little bit, just a little tiny bit about the continued fraction for pi. So unlike a lot of the continued fractions we've studied, the continued fraction for pi doesn't have any pattern to it.
Whoa!
Okay, well, let me get the eraser. Well, sorry, there are some continued fractions for pi that do have patterns to them, and I'll show you one of those at the end. But today we're just going to talk about the simple continued fraction. Oh shoot, where is, so about maybe there, is that on line? Okay. We're going to talk about just a simple continued fraction for pi that goes like this. 3 plus 1 over 7 plus 1 over, what you doing, sweetie? 15 plus 1 over 1 plus 1 over 292. Down, down, down. Whoa. Okay?
This equals pi.
This is pi. Now, but there's no pattern, so when I say plus dot 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 here, I don't even know what I mean. It just goes on infinitely far down.
To infinity.
All the way to infinity, but it doesn't. This one, this particular continued fraction, unlike the ones we've studied up to now, doesn't have any pattern. But we're going to do our magic continued fraction machine and see if we can get some interesting approximations for pi. So first we write down 3, 7, 15, 1, and 292.
Here's the box.
Okay. Yeah, we've got to be careful about that box. Okay, and then we're going to write.
Yeah, that's why I wrote it long.
1, 0, 0, 1. Okay. And let's see, 3 times 1 is 3 plus 0 is
3.
3. 3 times 0 plus 1 is 1. Okay. What's 7 times 3?
Is 21.
Plus 1 is?
Is 22.
22. And 7 times 1 plus 0 is 7. Okay. Alright, so here's our first thing. The first approximation for pi is just 3. So pi is about equal to 3. Can you scoot over just a little that way? That's what this says, 3 over 1. Also, a better approximation for pi is about equal to 22 over 7. Okay? That's what that says. Now we're going to find an even better approximation for pi. Are you ready?
Yeah.
15 times 22 plus 3 on the top. I guess I better erase here. So we got to do 22 times 15. How are we going to do that?
Well, 22 times 10 is 220.
So this is the same as 220 plus.
So what is 22 times 5? That's 110.
110. Very good.
Which is
so 330. And then we got to do 15. Oh, sorry. 330 plus 3. So 333 divided by 15 times 7 plus 1.
That's 106.
That's 106. Exactly right. Okay?
So
So pi is about equal to 333 over 106. Well, that's interesting. It's still not exactly right. It's only wiggly equal.
We gotta get the equal to be straight.
Okay, and now we're going to do one more. 1 times 333 plus 22. That's easy.
That's 355.
355 over 1 times 106 plus 7 over 113.
Yep.
So pi is also about equal to 355 over 113. Now we got to do 292 times 355 plus 333. Yeah! We're not going to do that. We're definitely not going to do that. So, but this is neat. It shows you a couple interesting approximations from the continued fraction for pi. And I was going to see if I had in this book here a different continued fraction for pi that was a little easier to understand. I thought I did, but I can't find it so quick. Hold on 1 second.
Okay. Are we ready yet?
I guess I'll just wait.
Okay.
Okay. So let's review what we've talked about. So we have our continued fraction that we just learned for pi, which is pretty neat. We learned about how to do simple continued fractions like, I don't know, 2 plus 1 over 3 plus 1 over 4. We learned how to evaluate that. You evaluate them from the top up, or the bottom up. So this is 2 plus 1 over 13/4, which is 2 plus 4/13, which is 30 over 13. So we learned how to do that. Then we looked at our special continued fraction machine, which told us how to evaluate the continued fractions from the top down. And that was kind of nice.
Yeah.
And then remember yesterday when we talked about the square root of 2? Which, do you remember what the square root of 2 is? It's a number. What special property does it have?
It's 1. No, it's square root of 2 times square root of 2 equals 2.
Right, yeah, and then this just happens to be equal to 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 all the way down. And so this was kind of a neat continued fraction, and we learned some approximations for the square root of 2. Okay? You all done? Hey.
Yeah.
You all done? So this is our last lecture on continued fractions. So we're going to go back to doing Olympiad problems unless there's some other topic that you want to learn a lot about.
Yeah.
Do you have one?
Not really.
Not really? You want to go back to doing Olympiad problems?
I'll think about it.
Okay, well, very good. Well, good job. Good job on continued fractions. I'm glad you suggested it. This was sure a fun week of doing lectures on continued fractions. All right, good job, honey.